we continue from this fictitious experiment we did last time involving uh, a thought experiment of Galileo, if we had access to Mathematica. Today what we will do is go a little bit further and see how we can do some data analysis on the obtained data. So we saw how we can do statistical analysis last time and to get error bars and so on. So if you already have the data with error bars with you, then and you have a good guess available to the form that a certain function must take, the data must behave according to a certain function, and then you can go ahead and do curve fitting to extract the most optimum parameters. Right, that's the content of the present lecture. Okay, so let's quickly recall what did we do last time. So we introduced this constant g, and then we describe, or we use this little piece of code to generate some spread around half gt squared. So I have used this random real, and then so I have data which is all these functions which are used in a nested form. So you can go back and check out that earlier video to understand all of these, and then you see that I have many pieces of data. So I have just chosen 5 here. Of course you can have more. Maybe let me make it 10 like last time. You can even choose 100. So it gives you so many columns of data. So in order to suppress all this information, then I can of course rerun it. Running simply involves shift enter. I can rerun it with putting this semicolon. All right, so then we have the first step, second step, and then we figured out how to systematically collect all this data in this form here. So we have this nth row and all columns starting from the second column all the way till the end, right? So this is the syntax: 2 semicolon semicolon. If you just don't mention anything at the other end, it's implied that it goes all the way to the end. And then you notice how we store the data for n, mean of the set, standard deviation divided by square root of the length of the set minus 1. So once again, this is a key point from last time we emphasized, is that the error bar is contained in the standard deviation divided by square root of the number of data points you have minus 1, right? And so if you have more data, then the error bars are going to shrink, right? So yeah, so this was the main message from last time, which we also managed to implement. And then you can go ahead and express this in a nice form using table form, and then finally you can also plot this data. So okay, so let's. So it says that there is a better newer version available, and so depending upon which version of Mathematica you are running, so you may need to use a different version, but this is something that you can easily figure out. It's simply a matter of what version of Mathematica you are running. So you will see that if you do this, you can extract error bars. So error bars are very tiny, so that's why it's not I have not exaggerated it like I did last time. So this is all some things that you will play and learn as you go along. So today what we want to do is, of course we know that this data is going to sit on half gt squared, right? After all, we have generated this data and created a spread, and then we have worked backwards to extract these error bars. But imagine for a moment that you were Galileo, were just still uncovering this law. This is the first time you're seeing something like this. You performed this experiment many times, and then you collected all this data, and you have this curve which looks like quadratic, but is there some more solid way of ascertaining this and systematic way of extracting some fit parameters, right? So that's the subject of our discussion today, right? So this is a slide on the basics of fitting theory. So actually quite a vast subject, and so some people spend a significant portion of their career, in fact, working on these kinds of models and figuring out optimum strategies and so on. And certainly this, if you want to do this in great detail, it would be a whole course by itself, and which is certainly not our aim here. So here we will just get a quick brief glimpse of how the logic which goes into extracting parameters. So here, for example, in our case, we know that there is a quadratic form to which we want to fit. Suppose you have some n data points, y1, y2, y3, so on up to yn, for x values going from x1 to xn, and let's say that each of these data points is associated with a certain, with error bars sigma 1, sigma 2, sigma 3, so on, sigma n, right? And if we already have some guess to make for the type of curve that must pass through this, let's say that you believe that it's a linear curve, it's a straight line that must pass through this, and you ask what is the best straight line which would correspond to the available data, right? So then of course we all know that a straight line is given by y equal to ax plus b. So we want to know what is the best a and best b given all this information. Can we use all this information and extract these quantities? And so one approach for this is the so-called least squares minimization criterion. So what you do is you go to every point and you compute the deviation from the linear form, right? So you suppose for the moment you don't fix a or b, right? So you just keep it as a variable a and b, or any number of variables in fact you can have in which are fit parameters. So then you form this function which is called x squared. So you find the deviation squared, and then every deviation must be measured in some units. And so the advantage of having all these error bars is that you have a natural scale to measure in, right? So you take these deviation squares and divide them by the variance at each of these points, or rather I should say the error bar squared, right? So if the error bars are sigma 1, sigma 2, so on till sigma n, you just divide by sigma 1 squared, so on, and then you just simply minimize over this function, right? So there's a lot of lines which will look like they are decent good fits, right? If you were doing it just by, you were trying to sketch a line, you could do it, but this method gives you a quantitative way of obtaining an optimum line which passes through all of these points, right? And so of course one can do more complicated functions. So in general, so this is what is called a linear approach, linear regression. It's linear in terms of the fit parameters, right? So in general, actually you can have more complicated functions sitting there. You can choose like a basis of functions, and then with parameters associated with each of them. So just like we have ax plus b, you could have a more complicated function involving ax plus b plus maybe c times x squared, or plus d times even more complicated functions. You can have any number of parameters, but it's going to be linear in all of these parameters. And so then this approach will work. But I mean you can have more complicated cases, like for example, if you want to fit your data to a function like exponential of lambda times x, and lambda is your parameter that you want to extract. So then it's no longer a linear fitting, it will become an exercise in nonlinear fitting, which is generally much harder and where there is much lesser control involved in the procedure. And so there is a lot of discussion on this. I'm just giving you a quick sort of overview of how these things go, but there are many times it's possible to convert these nonlinear type fitting into a linear fitting by for example the case that I just mentioned, exponential of lambda times x. If you want to fit to y equal to exponential of lambda times x, where lambda is the parameter, all you do is instead of fitting y with x, you fit log y with log x, and then it becomes linear in the variable lambda after this, and then you can go ahead and use basic least squares minimization type criterion, right? So like I said, it's not the objective here to go into any of these details, so we'll just use this as a prescription. So by the way, I should also mention that a lot of the times these error bars are not available. You don't have sigma 1, sigma 2, so on. In such a case, the standard practice is to just put all of them to be equal to 1. You simply minimize over the sum of these deviations, and that is also a legitimate approach which is carried out you know, in many of the inbuilt routines which are there in lots of programming languages, including Mathematica, which we will come to in a moment. So, but let's work this out the hard way first. So, let's do it for our Galileo's problem. So, before we do this, actually it's very nice, this function called manipulate that Mathematica has. So, what we can do is actually, so we already know that roughly this looks quadratic. So, can I take, so my goal is, I don't know what is this factor a with respect to which I should multiply x squared. So, what I will do is I will on the same graph show ax squared, you know, plot of ax squared, x going from 0 to, you know, this is just some syntax, and alongside I am also going to plot the data that I have, the data which has come from my numerical experiment in this case, but in general it can be hard data, right? And then what I can do is I can use this very nice feature in Mathematica to keep on changing this value of a, and I see that as I increase a, it seems that my data is coming closer and closer to the two of them are matching, right? And so it seems that if I had chosen my a to be 5.25, maybe around to 6 to 5.3, let's say, the fit seems to be very good. So I could just guess that my results are consistent with the expression 5.3 times x squared, right? So the whole point of this exercise is to see if we can do better, if we can make this more quantitative. And if you want to do that, of course, the chi-squared approach that I just mentioned is the way to go. And let's see how we can do it using Mathematica, do the hard way, right? So what do we want? Let's say we define an array. Table command is very useful, involving, so as a ballpark I just take it as 5x squared. It's 5.3, right? So but it's okay, let me just take 5x squared and generate a bunch of data, and I want to be able to compare this data with my mean data, right? So the mean data, this array has information from my raw data that I have. I also have error bars which are sitting in the third column, right? So what I can do is I can compare my mean data, first row 1 comma 2. So second column has all the information about you know, all rows and second column. So I create an array of this kind. So let me actually go over this step by step. So if I were to just take just one element, I can do mean data minus test function of 1. So the first number in this whole list corresponds to this first element of this matrix that I have, 1 comma 2. The first row second column corresponds to this. So I subtract this, square it, and then I take the error bar which is located in the third column, first row third column, square it. So it's exactly like the prescription which is described. So this is what I want to do, and I want to be able to do it for every element of this, for all the rows here, right? So I take my rows starting from the first row all the way up to the last row. So I put nothing to the left side or to the right side of these double semicolons, which means that I cover all the rows, and I go to the second column. So if you are a bit confused about this, go back and watch the earlier video. That's one way. And another is, of course, you can just search the documentation of Mathematica to figure out how to deal with these arrays, how to call these, you know, from which row to which row and so on. So the nice thing about Mathematica is that you can take this entire array and do these operations as if you're acting upon numbers, right? So if you take the difference of these two arrays, test func is an array, and then this mean data of all the rows comma second column is one array. So it will just take the difference of these two for each element, and then not only that, you can directly go ahead and square this whole array. And what does it do? Mathematica will automatically operate on every single element of this array, and then it's also legit to go ahead and directly divide by sigma squared, you know, of the whole array we are saying. but it will automatically take care to do this division for each element one after another in that order, right? It's very important. So if you were using some more, a language like C, where you have more control arguably, but also it involves more lines of code. So Mathematica is um, typically not as time efficient as a language like C or Fortran, but it gives you so much more convenience, and you don't necessarily need your code to be like super efficient for all applications, right? So there are certain contexts in which it's better to go to a language like C or Fortran or Python or whatever, or if you want something very quick, and particularly if you're learning programming for the first time, if you're just getting introduced to programming, for sure this is much more hands-on. Okay, so instead of putting in a for loop like you would in a more traditional type of language, you just operate like this, take an array, subtract two arrays, square an array, everything, all of these kinds of operations can be done. Okay, now what do we want to do to calculate? So I have said in this previous slide, so I have shown you how to compute the first guy, the second guy, the third guy. All the n guys are stored as different members of this array, which is called temp array. So in order to find chi-square, I just need to sum this array, and so simply invoke this function called total, and you're done. Basically, that's it. So now, of course, I want to carry this whole thing out in a compact way, and also store all this information for more analysis. So I will do all of this in one shot here, right? So you look at this. I define this entire operation as a chi-square data, and so this will create a table for me. It will, first of all, I will define f of x, this function f of x with x squared. A itself, I will take it to vary from 4 to 6. Already having used manipulate, I know that it's somewhere around 5.3. So just to be safe, I will allow my a to vary all the way from 4 to 6, right? So that's what this command does. I allow my a to go from 4 all the way up to 6 in units of 0.01. Then I will just carry out the same thing that I just did earlier here, but with respect to this function f of t, right? F of t is defined as it's the same function, but I'm allowing a to vary here. It's not here I had just fixed a to be 5, but I want to do it for a whole range of values of a, and I will just carry this same procedure out. It's mean data semicolon semicolon comma 2 minus table of f of t. Here I have f of t where t itself will go from 1 to 10. So I can directly do this instead of defining some test func called table is equal to table of this and all this. I can directly define table of f of t comma t1 1 to 10, and then it's understood that it's an array. I can subtract these two arrays, then I can take the square of this big array which has been formed, and then I can also go ahead and divide by the error bar square. All of this is done in one step. Very convenient, very compact code. And then I want to store this data. Finally, I care about a and chi-square, right? So that also is done here. So it creates a table of, so the first part here is doing some operations, not storing anything, but when you say put this in these flower brackets, a comma chi-squared gets stored, and the third flower brackets tell you what is the range of values that a takes. A varies from 4 to 6 in units of 0.1. So let me go ahead and run this. So there you go. So I have all this data has been created. So it is just, if it were 4, then my chi-squared is 4144.27, 4.01 another value, and so on. So I want to visualize this information. So let me plot this. So let me plot this. There you go. So there you see that it's not a surprise that around 5.3. So I can of course zoom in on this. I have all the data here. For any value of a, I can go ahead and pick up the chi-squared. So then I would go to the minimum here and identify that as the best fit using linear regression approach, right? So so there are ways of defining some notion of an error bar for A itself, and that error bar would be some some percentage increase in chi-squared about the minimum point and so on. So that's the advantage of doing it the hard way, is it also gives you some idea of not only an estimate of this parameter, but also you can get some spread around it as well, right? So the theory is quite involved, so you can do more complicated fancy things like goodness of fit parameters and so on, but let's not go into any of that here. So our goal here is to show you that there is a simple prescription. We just told you what that prescription is, and then we told you how using Mathematica you can actually go ahead and carry out this implementation yourself. You could play this type of a game out for some other experimental data that you have. You can just import all that data, and then you have a functional form to which you want to fit. First you have learned how to get error bars. Do that, use all of this and make your own chi-squared data and get your own error bars, right? This is one way of doing. This is also a very nice way. Manipulate is an approach where you directly get to that number. There were no error bars here, of course, but here you have some more information. Chi-squared is perhaps the most rigorous way of doing this kind of an analysis. And then the third way is to just go to Mathematica and say, you do this for me, right? So there is an inbuilt function called fit. Fit is also it uses this kind of a linear approach. So I said that when I defined chi-squared, I was trying to fit it to a functional form of the kind a plus bx, right? So in general, actually this linear method can work for a times basis function f1 plus b times basis function f2 plus c times basis function f3, so on. So this is as general as it can get, and all these basis functions can be very complicated functions. They can be highly nonlinear, they can be whatever, and it would still come under this linear fitting, right? So that's what is going on here. So we can take 1, x and x squared as its basis functions, and then we have this whole data in here, the first part, comma, separated by the basis functions. It could be 1 x squared. You can play with this, you can put in x cube, you can put in whatever else, and then the final thing is to just say that you're fitting with respect to so the independent variable is x. So if I were to do this, I get an answer like 3.2509 minus 1.876, so plus 5.48. So this is doing a fit and giving me some non-zero values for the first two numbers as well, right? So this also tells you that one has to be careful with fitting. You can fit your data to more than one type of function. So purely based on fitting, one should not come to their conclusions. All the inference should not hinge purely on fitting to a form which looks like the correct form. There must be some independent way of checking this. So let's do this. I mean, in our case, of course, we know that this should involve only x squared, and then of course you get some value like 5.3, right? So we can go ahead and check how this if I were to use this value of this parabola of x with this fitting form and compare it against my original data, and of course it's not a surprise that the two of them agree very, very closely. And also our own eyeballing exercise using manipulate also gave us a number around 5.3. So you can go ahead and check how far away. So with this analysis, you are really getting at g, right? It's g by 2. So g by 2 we know should be 9.2 by 2. G is equal to 9.2. So let's see what is the percentage error in our experimental determination of g, and it's not too bad, and that of course has to do with the error bars we had chosen. So we had chosen error bars of 0.01, 0.15, which is actually not too small. So in the end, it's I guess it's a decent outcome for our numerical experiment. But anyway, so the main point of this this lecture or this module is to illustrate the method, right? So the method is, first you have the data which has come in because you already know how to compute errors, and then you can use this alongside the chi-squared minimization approach. You have to come up with a sensible guess for the functional form, right? So this is something which sometimes would involve some other kind of intuition. It's not purely based on how the graph looks. Sometimes it can be, but it should be buttressed, or it should be supported. It should be supported by some alternate intuition or some other argumentation. And then once you have a functional form which you can depend upon, this only tells you what is the best set of parameters which can give you this, which would fit with the data. So finally, I want to give you a brief description of how the same thing can be carried out using a nonlinear fit. So if you can take any function here. It doesn't have to be, x or x squared, or you can take any much more complicated function and fit it with respect to an exponential form, a logarithmic form, or whatever you want. But like I said, the control involved in the algorithm which goes into generating this fit. So here I am going to just use a function called FindFit, which comes inbuilt in Mathematica. Here there is no notion of basis functions or anything. It's just one big complicated function you give, and FindFit will do it for you, right? So you can ask it to fit it to the functional form a plus b, bx plus cx squared using the parameters a, b, c. That's the syntax. And then you have to also say what is the independent variable here, x, and you can just go ahead and implement this. So it tells you that a must be around 3.25, b must be this, and so on. So here also, of course, we could have fit it to just cx squared if you wanted, right? So if you can do this, and then we say that so use of FindFit for this kind of a fit would be a bit of an overkill, but it's possible. So let's check how that would. Okay, so I guess it's not very happy. So let's check what happens if you do bx plus so I think the issue was just with the gap between c and x squared. So this should work out. Let's also clear this. Okay, there you go. So it's giving us 5.3, which is what we had from the earlier method also. So yeah, so now you have to use this syntax. So use the number which has come out of this fit, and in this function fn of x, and then there you go. So then we can plot all of this, and it's not at all a surprise that the data will sit on top of the experimental data, the raw data that we have. Yeah, so this is just a summary of this whole lecture. What did we do here? First thing is we come up with an intelligent guess for the functional form, having got the data and got the error bars using the prescription from last time. Second is we try out the manipulate function, right? So you could have more than one fitting parameters, and so you play with all of them and zero in on some ballpark of these various parameters in which your data is likely to fit with the functional form. And then you can either use fit, which is a Mathematica program which can directly do it for you, which is a linear fitting program, or you can do more complicated function like FindFit, which is a nonlinear one and should be avoided as far as possible because they are not so stable, right? So it's better to do linear fitting and it's better to convert problems which involve nonlinear fitting into linear ones if whenever it's possible by for example doing some kind of a transformation, right? So I did not go into any of that, right? So I'm just telling you the various options. So there is fit or there is FindFit, and then but of course the most sort of controlled approach is for you to sort of directly do it by calculating chi-squared, because you have all the error bars. So if you notice, we did not feed in any information about the error bars to Mathematica here. So surely the chi-squared approach has more information in it and it controls it even better. Okay, so what does the chi-squared approach involve? So you simply compute this chi-squared as a function of all these parameters a, b, c, d, how many ever you want, and then make a plot of this function as a function of all these parameters and find out the point where it has a minimum. And you can define some kind of an error bar in these parameters based on the percentage increase or chi-squared. There is a whole systematic approach to do that as well, but for our purposes, just getting at the minimum itself is what we want. We have the parameters and then we have some understanding of how the chi-squared increases around these points. Okay, so that's this lecture. Play out these techniques with some other data that maybe you got in the lab, or you can try out similar numerical experiments, come up with other similar phenomena, extract your own data, create your own data, and then analyze them. Thank you.